So we started by building a full ER simulation to track how patients move through the system and where delays actually form. Our goal as a team was to understand bottlenecks without changing real-world operations. The model follows patients from arrivals to discharge or admission, and it gave us a clear baseline of how the ER behaves under pressure. As a group, we mapped the full ER workflow into Arena, like the arrivals, triage, beds, nurses, physicians, and diagnostics. Once we simulated it, the big takeaway was that physicians, beds, and diagnostics are the main source of congestion. That baseline let us collaborate on testing different improvements later on. Patients arrive every 9 minutes on average and get assigned one of the five triage levels. The first stop is a bed check since there are only 12 beds. High acuity patients may go right in, lower acuity patients go through triage first. Getting this stage accurate mattered because early delays rippled through the whole system. Here, we focused on LWBS for levels 1 and 2 patients. Those are the only ones who leave immediately if they found that no bed is available. What we saw is that LWBS isn't quite random. It's tied directly to how well resources are allocated downstream. This helped us connect bed shortages to system-wide congestion and guided our later scenario choices.
The triage entry process consists of the triage entry, the triage process, bed seizure, and then room entry. Triage entry for non-critical patients, which are patients level 3, 4, and 5, always proceed to triage when no bed is available or even if a bed is available, but they must still be triaged first. For patients level 1 and 2, they either skip triage and go directly to a bed, or they leave without being seen if no beds are available. After room entry, the first registered nurse will assess the patient. There are 6 registered nurses to assess the patients, and it each takes about 2 to 6 minutes. After this, the patient will wait for a physician. The physician exam and the bed release will be next. A physician will evaluate each of the patients with service times determined by their acuity level. Level 1 will have a mean of 120 minutes with a standard deviation of 30 minutes. Level 2 will have a mean of 60 minutes with a standard deviation of 15 minutes. Level 3 will take between 2 and 50 minutes. Level 4 will take between 10 and 30 minutes. Level 5 will take between 5 and 20 minutes. Once the physician visit ends, the patients will be released from the bed and transferred to a non-limited seating area for diagnostics. Next is the diagnostic processing. Patients will undergo diagnostic tests depending on level-dependent probabilities as shown in the chart below. We are assuming that lab tests will typically require 30 minutes plus an additional processing time. X-ray processing will take about between 20 to 60 minutes based on procedures, and CT scan processing will typically require 40 to 90 minutes of processing time.
So as it pertains to our final RN visit, one of the final components we added to the model was the final RN visit. This step represents the last clinical evaluation a patient receives before either being discharged or admitted. At first it seemed like a small addition, but modeling this correctly was important because the RN team is already used heavily throughout the system. Using the triad distribution helped us capture the variability we observed in real-world nursing evaluations, which aren't always consistent. In the process, we realized how sensitive downstream flow is to even short delays at this stage, especially because we only assigned 6 RNs. So this part of the model helped us understand the impact of final checks on overall throughput and patient progression. When it comes to disposition at admission, This decision uses the level-based admission probabilities that were already given to us. Our main task here was implementing those probabilities correctly so that each patient level followed the appropriate path. For the admission processing time, the Expo 15 distribution was something we assumed based on typical administrative durations. Once we added it, we noticed how even a modest processing time could affect the wait-to-bed queue. This part of the model showed how sensitive the system is to bottlenecks in paperwork and bed assignment. Now let's talk about animation. This is one of our primary focuses throughout the whole project. This is where the model really came to life and where we gained the most insight into what was happening moment to moment. Building the animation wasn't just for visuals. It helped us diagnose system behavior. For example, the queue graphs for lab and x-ray immediately reveals where bottlenecks were forming. Without the live plots, we wouldn't have been able to notice how often patients were piling up during peak arrivals. The triage and admissions indicators, especially the green to red status changes, made it easy to see when staff were idle versus fully utilized. That visual cue helped confirm that certain delays weren't resource shortages, they were routing delays. The bed usage icons were also incredibly useful. As soon as the bed limit was hit, the animation made it obvious that patients were backing up into earlier stages, which support our findings on LWBS rates. And finally, the live counters for busy physicians, occupied beds, admitted patients, patients leaving the system, and LWBS gave us real-time performance feedback. This was especially valuable during scenario testing because we could visually verify that the changes we made were actually improving flow. Overall, the animation became the best diagnostic tool we had. It helped us confirm whether our logic made sense, whether our distributions were behaving reasonably, and where the true bottlenecks were occurring.
Now with the scenario analysis, in our tests, we found that physician staffing and bed capacity had the biggest impact on how the ER performs. We also tested two system flow designs to see how changing the process would affect results. Scenario C, the fast track for level 4 and 5 patients, sends low acuity patients through the system without taking a bed. This feeds some beds, but it pushed the bottleneck to the physicians, labs, and imaging areas. Because of that overload, the length of stay went up around 171 minutes, even though the left without being seen improved. Scenario D, the point of care testing model, had the lowest length of stay at about 123 minutes. But since patients stay in their beds while lab work is done, beds are released much later. This caused the left without being seen to jump to 203 patients, which is far above the baseline of 95. So even though the length of stay is great here, the access problem makes this scenario unrealistic. Now with the best scenario, when the goal is specifically to reduce left without being seen, Scenario C is the best option, as it lowers left without being seen by a large amount and it keeps queues under control. Even though length of stay increases, the improvement in patient retention makes this trade-off reasonable. If we only look at staffing changes, the strongest and the most balanced setup is adding 2 physicians and 1 bed only. This scenario gives some of the lowest length of stay values in the staffing group, and it keeps queues stable and also produce some of the left without being seen numbers without needing to redesign the system. So overall, scenario C is the best for reducing left without being seen, and adding 2 physician and 1 bed staffing setup is the best for steady, efficient ER performance. To conclude, our simulation showed how strongly physicians and beds shape the ER performance. Small changes to these resources quickly shift bottlenecks and affecting both length of stay and how many patients leave without being seen. Overall, the model helped us to understand how the ER behaves as one connected system and why balanced resource allocation is key. Thank you for exploring our ER simulation with us.
Here is a front-end look at how our simulation tracks metrics and shows animations.